Welcome, everyone, to the second episode of The Abstract, the neuroscientific podcast where we break down the latest in neuroscience research into four parts: objective, methods, results, and significance. I am your host, Shahin Zagros, and today I'm joined by a very, very special guest, Dr. Sara Larivière. She's an assistant professor at Université de Sherbrooke and the principal investigator at the SLIC, which stands for the Sherbrooke Laboratory for Integrative Connectomics. Dr. Larivière holds a Canada Research Chair in Neuroimaging of Epilepsy, and she has published numerous high-impact peer-reviewed articles in top scientific journals, one of which will be the topic of today's discussion. Beyond all her academic accolades, she's also a good friend of mine, a colleague, and a former lab mate. In fact, I had the pleasure of working with her for many years at the MICA lab at the Montreal Neurological Institute. And since then, she's gone on to establish herself as one of the rising stars in the field. And it's truly an honor for me to have her on the show today. So without further ado, Sara, merci d'être ici. How goes it, homie?
Merci, Shaheen. I'm very pleased to be here. Thank you so much for having me. Things are good. Things are really good.
Fantastic. So, Sarah, why don't you maybe start off by telling us a little bit about who you are and how you came to be interested in the brain, and then maybe talk a little bit about the kind of research that you're currently conducting.
Mhm. Well, I think you covered a lot of who I am, actually, but something that wasn't in the introduction that's I think it's important to notice or to note is that I'm a big fan of epilepsy research, and there's a very deep personal connection for this. And it's because I grew up with a brother who has epilepsy and has had epilepsy for all his life. So I was really into that environment from a very young age. And in the case of my brother, he had pharmacoresistant epilepsy, so medications just would not work for him. And when he was 18, he was referred to the Centre Hospitalier Universitaire de Sherbrooke, the CHU in Sherbrooke, where I now work. And the neurologist there suggested that he should have a brain surgery, to treat his epilepsy. So he underwent surgery and then was seizure free for 15 years. And we could see all the amazing changes in his life and his quality of life and his behavioral and cognitive abilities, in addition to being just able to live seizure free for a very long time. And then, 15 years later, I get hired by the same university I get to work with the same neurologist that treated him. So to me, it's really a full circle, and hopefully I can help other families that are going through the same thing my family and I went through all these years ago now.
That's wonderful. And we wish your brother and yourself continued success and health. It's a nice story. So today, as you know, we'll be discussing a paper that we published back in 2024 in the Journal of the American Medical Association, JAMA Neurology, and it pertains to epilepsy and neurostimulation. Now, you were the lead author on this project. I myself contributed as far as the neuroimaging data acquisition is concerned. The title of the paper is, quote, Brain Networks for Cortical Atrophy and Responsive Neurostimulation in Temporal Lobe Epilepsy, end quote. Now, Sarah, before we jump into this paper, I just wanted to share with our viewers and listeners a quick tidbit about epilepsy. Now, epilepsy is one of the oldest documented human diseases. There's an ancient Akkadian record that dates back to about 4,000 years ago that describes what appears to be someone having a seizure. I have the English translation here. Quote, his neck turns left, his hands and feet are tense, and his eyes wide open, and from his mouth froth is flowing without having any consciousness, end quote. The document also associates epilepsy with the hand of Sin, Sin being the Mesopotamian god of the moon. And interestingly, this link between the moon and epilepsy is somewhat pervasive in human history. The Greeks, for instance, they attributed it to the moon goddess Selene or Mene. And for the longest time, people used to think that the full moon or or the new moon was the primary cause of epilepsy. In fact, as early as the 19th century, Dostoevsky, the famous and highly touted Russian wordsmith, who suffered from debilitating bouts of epilepsy, he wrote in a letter to his brother, I quote, in general, he's referring to his physician, in general, he advised me to beware of the new moon, end quote. So let's start maybe with a preliminary question to ease our way into the science. Um, what is epilepsy, Sarah? And more specifically, what is temporal lobe epilepsy and why should we study it?
Yeah. So I think epilepsy is it's quite commonly known, but it's also very widely misunderstood for some reason. I think people don't exactly know what epilepsy, or they have an idea of what epilepsy is that may or may not be truly what it is. So epilepsy, it's a neurological disorder. It's characterized by unprovoked recurrent seizures, and it's the most common chronic neurological condition in the world. So it affects about 1% of the population. So roughly maybe 60 to 80 million people worldwide today. And temporal lobe epilepsy is a specific form of focal epilepsy. So it's the most common one in adults. And it has seizures that originate in the temporal lobe of the brain, oftentimes from a very specific brain region. And that's why we call it focal epilepsy. And that region is the hippocampus, which, as you know, Shaheen, is very essential for many cognitive and function, especially memory.
Yeah. 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 So it's a you also mentioned your brother. It's a type of pharmacoresistant epilepsy. It's one of the most common ones, and I think something like 30 to 40% of individuals who are diagnosed with epilepsy, they will not actually respond well to conventional treatment with anti-epileptic drugs, and a large portion of these individuals will be diagnosed specifically with temporal lobe epilepsy, which, as you mentioned, affects the temporal cortical areas.
So yeah, that's right. There's your numbers are correct. There's about 30 to 40% of people with temporal lobe epilepsy that just do not respond to medication, however many they try. And this is a big challenge in clinic, but also it offers a potential research avenue for researchers and science to try and find the answers for these patients, these pharmacoresistant patients. And one of the answers is to look at other sort of treatments for their epilepsy, whether it's neuromodulation, dietary, neurosurgical approaches. So yeah, there's a lot of options, but the challenge is that we still don't know very much about how these operations or these treatments affect the human brain.
The paper we'll be talking about today is a step in the right direction because there's a lot of themes that you mentioned that are covered in this paper. So let's jump right into it. So what we'll do is we'll go over the we'll basically dissect this paper into four components. So objective, methods, results, and significance. And after that, we'll have time to answer a couple of questions that were submitted by our viewers. So, what was the main goal of this study, Sarah?
So this is the study that I carried out during my postdoctoral fellowship with Dr. Michael Fox at Harvard. And what we were really interested in at the beginning was uh, looking at TLE from both a focal perspective. So there's in TLE there's damage to the hippocampus, like we mentioned before, but we also see these damage elsewhere in the brain that are in regions very distant from the hippocampus. And that kind of prompted a shift towards considering TLE as a network disorder as opposed to a disorder of a focal brain region. So, in an attempt to try and resolve these two perspectives, the focal epilepsy versus the epilepsy as a network disorder, we wanted to look at is there any link between the hippocampal damage and the damage elsewhere in the brain. And I was very fortunate to do my postdoc with Mike, and he and his lab created this novel approach called network mapping that we'll talk about later, I assume, that really just allowed us to kind of bridge these two views together and provide some answers.
Back in 2019, we published a review that kind of uh, talks about how, in light of new developments in analytical frameworks, especially with regards to connectomics and also the implementation of powerful new neuroimaging modalities, it appears that more and more epilepsy and temporal lobe epilepsy seem to be construed more as a kind of like network level disorder of the brain, as opposed to just the focal lesions in the hippocampus, etc.
Yeah, absolutely. I think, and a lot of the treatments now are kind of heading in that direction too, with neuromodulatory and neurostimulation approaches being very increasingly used to treat epilepsy.
Yeah. Okay. So this project was an international initiative. It included multiple sites where data had been acquired. So can you tell us? I mean, obviously it involves temporal lobe epilepsy or TLE patients, but could you maybe describe more specifically what population cohorts were selected and studied in this project?
Yeah. So, like you mentioned, we were very fortunate to be able to work with people all around the world, and people in epilepsy research and especially neuroimaging of epilepsy are extremely generous and always, or most of the time, very willing to collaborate, which is amazing. So, for this specific study, I think we included something like 94, 95 TLE patients, as well as 120 healthy controls from 3 different sites. So, we collaborated with Boris Bernard at McGill University and the MNI. Yeah, we had also had data from Luis Concha from Mexico, and also data from China from Chiqiang Chang at Nanjing University. So a very very large sample size, I think, for this type of study. And we also had to add some clinical meaningful interpretation into our study. We also had access to a local in Boston 38 patients that underwent responsive neurostimulation as a treatment of their seizures. So this is a type of neurostimulation surgical approach that patients who are not necessarily candidates for resective surgery can use. And then on top of all these data, we also had access to functional connectomes from 1,000 healthy controls from an independent site, which served as our sort of baseline control group for the network analyses.
All right, good stuff. So, what neuroimaging modalities exactly were acquired, and maybe speak to the measurements that were derived from each modality?
Mm-hmm. Yeah, so we were a bit ambitious in this study. I think we um we we tried to get as many different sequences on MRI as we could. So we had one T1 weighted scan, so it's an anatomical or structural MRI scan that contrasts the gray matter and the white matter in the CSF, and we use that to look at the thickness of the gray matter, so how thick that gray matter ribbon around the brain is. And then we also used something called diffusion MRI, which is kind of summarizes how water moves in tissue, especially in the white matter. And we use that to compute 2 different metrics called fractional anisotropy and mean diffusivity, which are used to characterize damage or the organization of the white matter tissue. So on the one hand, we had a measure for gray matter, and the other hand, we had a measure for the white matter. And then that cohort of 1,000 people also had functional connectome scans, so resting state functional MRI scans, which allowed us to look at how different regions of the brain communicate with each other and create this kind of map of functional connections in the brain. And then finally, the patients who underwent RNS, or responsive neurostimulation, also had a structural scan, so we could see where the electrodes were implanted in their brain after implantation.
Reading the paper, there's a methodological step that seems to be kind of like the basis of all the ensuing analyses, and that pertains to the generation of these individual atrophy maps for the hippocampus. Could you briefly discuss what these hippocampal atrophy maps are and how they were derived?
Mm-hmm. So in temporal lobe epilepsy, one of the signs we see on imaging is atrophy of the hippocampus. So the affected hippocampus, the one where seizures start, tends to shrink, and we can see that clearly on MRI most of the time. And so to try and quantify that, we computed the normal or average thickness of the hippocampus in all of our healthy controls, and then we compared our patients to these controls. So we knew exactly where in the hippocampus the patients had smaller cortex in the hippocampus. So we could very much pinpoint where in the hippocampus we could see the damage. And this is an approach that's a statistical approach that's validated now, and it's called W mapping or W scores. And what's great about this approach is that it allows us to control for different factors like age and sex, for instance, that could impact our results.
Is this the approach that you mentioned earlier was developed by Michael Fox, or
Yeah,
at
it's like the first step of his approach. Yeah.
Oh, okay, okay, wonderful. And so based on these hippocampal atrophy maps, you were then able to derive hippocampal atrophy networks using these resting state functional connectivity data derived from healthy individuals. Okay, could you maybe walk us through this process a little bit?
Yeah, of course. Yeah, so the idea was once again to kind of link the damage in the hippocampus to the rest of the brain, right? So to do that, after we identified the areas that were atrophied in the hippocampus, we turned to that cohort of 1,000 subjects and we look, okay, in the normal healthy brain, where are these areas connected to? So we looked at areas that are positively connected to the areas in the hippocampus that are damaged. So these are regions that tend to activate or fluctuate at the same rate or same phase and sequence as the areas in the hippocampus. So that created a sort of like positive network. We can call it the red network. And then on the other hand, we also had these areas that had sort of the opposite phase. So that when the hippocampus was activated, or activity went up, then these other set of regions went down. Their activity decreased. So we can call it this negative network, so the blue network. And so with these two networks, we had sort of a framework to look at, okay, so there's damage in the hippocampus, and then we have two whole brain networks. What happens in these networks?
Super, super cool stuff, Sarah. What about um, microstructure and morphology? I know the paper also mentions that there were specific analyses that were done to look at superficial white matter and also cortical morphology. Can you maybe speak to the effect of what these analyses were?
Mm-hmm. Yeah. So in temporal lobe epilepsy, we do see these sort of structural changes that are kind of widespread in the brain. So we see cortical atrophy, obviously in the hippocampus, but we also see cortical atrophy in regions that are far away from the hippocampus. So in like frontal-central regions, for instance. We don't really know why that happens. There's multiple theories, but we're not entirely sure why that's happening. And then we also see white matter integrity changes that are in different areas of the brain. They're most oftentimes in the temporal lobe, and they extend kind of away from the hypothesized seizure onset zone in the hippocampus. So we see these two patterns that are in one in the gray matter and one in the white matter, but they don't necessarily overlap. So they're in two different sets of brain regions. And what was cool is that once we had our blue and our red network, we could overlap these networks with these gray and white matter changes that we observed, essentially. So we had a framework to overlay our thickness changes and our white matter changes onto these two different networks.
Yeah, it's there's like a synergistic essence to how these two different um, metrics are associated in temporal lobe epilepsy. White matter white matter and cortical morphology. And we'll get into the specifics of it uh, in a bit. But maybe just to finish off the methods section, you guys also looked at the effectiveness of RNS, of responsive neurostimulation, as far as like seizure symptomatology goes. Let's maybe finish off this section with a conversation or a discussion about how the effectiveness was addressed.
Yeah, so RNS is like I mentioned earlier, it's a surgical approach to treat epilepsy, and it works by implanting electrodes in the hippocampus of these patients, and that these electrodes they kind of detect abnormal brain waves in the brain, and they respond to it by stimulating areas of the brain with electric pulses, and that's meant to sort of modulate the network connected to the seizure onset zone in an attempt to reduce seizure frequency. So when we talk about effectiveness of RNS, what we essentially mean is if you if a patient, for instance, had 10 seizures a week before implantation, and then after implantations they now have 5 seizures a week, then we say they've had a 50% seizure reduction rate. So if they went from 10 to 0, then it's 100% seizure reduction rate. So we express this in terms of percentage. So it's not so clear cut. It's not yes, still have seizures, no more seizures, but rather okay, has the seizures decreased in frequency, and then we express this as a percentage as a way to compute the effectiveness of this surgical approach.
Okay, and okay, so going back to your red and blue networks, your positive and negative hippocampal networks, what regions of the brain like made up each one of these networks?
Yeah, so the red positive network, the one that sort of functionally activates or co-activates with the hippocampus, was made up of a very well-known network. It's called the default mode network, and essentially it's these temporal, limbic, medial prefrontal, precuneus, inferior parietal cortex regions that make up this big, very dominant network in the brain that's often associated with rest periods or mind wandering or anytime you're a person is sort of thinking to themselves or at rest. Usually, we see this peak of activation in this specific network. And the opposite network, the blue network, actually is something that my postdoctoral mentor, Michael Fox, explained in a very well known PNAS paper, now, I don't know, like 10 or 15 years ago, about how there's this balance between two specific networks, the default mode network on one hand, when that activates, there's another network that's opposite of it that deactivates. And so the negative network in this case, the blue network, is a network of frontoparietal regions that's often associated with more outward behaviors like think or task or whenever you're doing something or you're paying attention to something, and your brain naturally kind of goes into one network and then out of it and then into the other network and then back to the it really it very much fluctuates naturally between these two networks, which turns out are both related to the hippocampus but in opposite direction.
Off of this explanation that you gave, the paper mentions this double dissociation that was observed between microstructure and also morphology, which kind of like speaks to like how I mentioned this like synergistic effect that you have, you know, your DMN, you have your frontoparietal, and they're both kind of affected, but in seemingly different ways.
Hmm. Yeah, exactly. So we observe this sort of cortical atrophy outside of the hippocampus that was in a very specific set of region, which turns out overlapped nearly perfectly with that blue negative network. So not necessarily the regions positively connected to the hippocampus were atrophied. Rather, the network that was opposite of it atrophied. And then on the other hand, we saw these changes in the white matter that were directly overlapping with that positive red network. So regions that were connected to the hippocampus showed, or in a positive way, showed white matter damage, but not necessarily atrophy. Yeah. So the thinking we had was that, if seizures start in the hippocampus, naturally it should propagate through the same set of regions that are positively connected to it, so that red network, and that network shows white matter damage. And then the opposite network, the network that kind of tries to maintain the balance in the brain, is showing signs of atrophy, perhaps in a sort of compensatory way, where it tries so hard to maintain this balance in response to seizures that it becomes kind of burnt out and atrophies over time.
That's fascinating. And what regions of the brain were these changes for both white matter and gray matter most pronounced?
Yeah, so we did both a group level analysis, so we looked at all patients kind of clumped up together, but we also looked into each patient separately, and the findings were very similar in both cases. So we see atrophy really in these fronto-central regions, a little bit in the temporal lobe because of the hippocampus, whereas changes in the white matter were more strongly located in the temporal lobe, and sort of the whole temporal lobe, and extending or sort of dissipating as it went away from the hippocampus.
Maybe let's finish off the results section by talking about the association between RNS, so responsive neurostimulation, and the hippocampal networks.
Yeah. So RNS is it's really interesting, and like all these neurostimulation approaches, like deep brain stimulation, for instance, that's widely used for a range of neurological disorders. We, we still don't know how they work, right? So we know if we stick electrodes in a patient's brain and we send electrical activity, somehow the symptoms dissipate, or even um, or improve. But we really don't know why. So, in search of some answers here, what we did is we looked at, okay, so there's electrodes in the hippocampus that sends electrical current. These electrodes, surely they are connected, or they send electrical activity to the hippocampus that are connected to specific regions, right? So it's not localized to the hippocampus, it sort of propagates throughout the brain. And it turns out people who had electrodes that connected to that blue network were doing much better after RNS implantation. So there are some key hubs like the insula, and I think it was the left SMA in the brain, that if you had electrodes implanted that stimulated the hippocampus that was connected to these regions, then you were doing much better uh, in terms of seizure frequency, which was quite interesting. So it kind of gives us a little bit of a glimpse of, okay, how does RNS work in terms of a network perspective.
So if you were to wrap up the significance, what would be the main takeaways from the study?
Yeah, well, so I think so. Focal epilepsy, like TLE, is not purely focal, but it's also not purely a network disorder. So there's damage locally and there's damage elsewhere in the brain, and you can reconcile these kind of two perspectives using network mapping. So these functional networks, these two networks, sort of tell us the whole story in a way of where we can expect to see white matter damage, gray matter damage, and also tells us, hey, look, if you implant with RNS in the hippocampus, well, you can also look into these networks to see if the patient is doing well or not in terms of their connectivity. So it really gives us sort of a localized and a network perspective to understanding TLE. And then clinically, it also hints at the possibility that we could look beyond the hippocampus and wanting to treat these patients that are perhaps not necessarily candidates for resective surgery that usually targets the hippocampus. But perhaps we can implant electrodes in the hippocampus, or we could implant electrodes in these regions that show a successful or a successful outcome in RNS. So is it the left SMA, the insula, or we could even use these findings to make sure before implantation that the electrodes are going to target the right set of regions for maximum efficiency.
Based on these findings, like what future research questions would you like to pursue, or have you been pursuing basically, what other new avenues does this paper open up for future investigation?
I mean, yeah. Like I mentioned, this was my postdoctoral work, but I liked it so much that it kind of became the foundation for a lot of projects in my lab right now. So starting off of this project, and I have a master's student. His name is Bintan Nguyen, and he's very very good, and he's kind of looking at it uh, backwards. So he, instead of starting from damage in the hippocampus, he starts with the damage in the rest of the cortex, specifically cortical atrophy. And he looks at where the atrophy is in the brain and looks at whether or not it connects to the area of the brain that gets eventually resected in these patients. And his hypothesis is very clear. Is basically is if you have atrophy that's negatively connected to the brain that eventually gets resected, then patients are going to do well after surgery. Whereas if you have atrophy that negatively connects to regions outside the surgical cavity, then these patients do not have a good outcome. And the idea behind this kind of goes back to this compensatory hypothesis where atrophy compensate for the area of the brain that kind of causes the seizures. So if it's not compensating or it's not directly related to where the area of the brain that gets resected, then you're resecting the wrong area. So this is underway. He started, I think, in June, and he's got like a very very large sample size of TLE patients from, once again, a lot of people around the world. So it's very exciting. Maybe I can come back for like episode, I don't know, like 38 and present these results.
I would love to have you on again. But this initiative sounds very very interesting, not just for like intervention as you mentioned, but also possibly for like prognosis.
Yeah, exactly. It's really something that's missing in epilepsy when a family or somebody with epilepsy comes to the clinic and they get offered this very invasive brain surgery and they're scared and they don't know what to expect, and perhaps they think they're going to have some cognitive deficits or they fear death or all these things, and then they ask like what's going to happen to me after you take out part of my temporal lobe. And unfortunately, as it stands right now, all the answer is we don't know. We don't know. We simply do not know. And this is extremely frustrating for a lot of the families and patients um, wanting to be seizure free. So with this work, hopefully we can provide some answers as to, okay, well, if based on what your brain looks like before surgery and based on the planned surgical site, then your chances of surgical or seizure freedom are 82% or 90%. And so there's a lot of hope in that work.
Well, thank goodness we have bright individuals such as yourself working on this very very important topic. Wonderful, Sarah. We blew right through the paper. I think now maybe we can answer some questions that were submitted by our viewers. Yeah.
Yeah, yeah.
All right. Let's do it. So the first one, this is a question that was submitted by user Armin, and it's a very simple question, but I think it goes at the heart of network neuroscience and connectomics. So he asks, what's the difference between structural connectivity and functional connectivity?
Yeah, it's a very good question. So structural connectivity kind of refers to the physical wiring of the brain. So when we're talking about structural connectivity, we're often referring to the anatomical pathways, so the white matter tracks that link one region to another. And these connections, we can usually measure them using diffusion MRI, like we've used in the work we talked about today, but not so much to describe connectivity, but other properties of the white matter. But you can also do some tractography to get these kind of nice looking multicolor figures that tells you where the tracks are and where they're going. But you can also do some postmortem histology or track tracing studies to look at these anatomical pathways and get a very good understanding of the structural connectivity of the brain. In contrast, functional connectivity describes more like the coordinated activity between brain regions. So it really reflects how two areas uh, signals kind of arise and fall together over time, or if they're even if they're not necessarily directly connected by this anatomical pathways. So using functional MRI usually can see more distant and broad networks that are what we call polysynaptic, so not necessarily directly linked between or linked together by white matter fibers. And tools like or sequences like resting state fMRI, MEG, EEG can also infer some type of functional connectivity between brain regions.
The next question actually pertains to autism. Now, I know it's not specific to the topic that we discussed today, but as someone who's examined this, who has done a lot of extensive work in autism, especially in the context of atypical brain development, I think you're a prime individual to ask this question. So it's from user Tim, excuse me, and he asks, how do you view the distinction between neurodiversity and pathology in the context of autism? And what significance does this framing have for understanding and working with autistic individuals? So basically, he's saying there are two schools of thought. One, autism is pathology. The second, autism is kind of like an organic divergence from the norm. And so, how do these two schools of thought basically inform individual patient care?
Well, that's a really tough question, and yeah, like I've done some autism work before, but I haven't looked at that field in many years. So it's kind of hard for me to answer honestly, but I think one does not necessarily exclude the other. So I think there is some neurodivergence in autism. So you do see something of a like a trajectory that kind of diverges from the norm. But you can also see some type of pathology, whether it's uh, atrophy or hypertrophy or white matter changes or disorganization in the brain that in epilepsy, for instance, are considered pathology. So hippocampal atrophy is a pathology in this case, and it's secondary to sclerosis or something like that. But I don't think that I don't think that it's so clear cut that it's one or the other.
Um, I have maybe two more questions. The next one is from user Apex Rose. He asks, what's the most surprising way you've seen large scale network connectivity change in response to experience or training?
Mm-hmm. Oh, that's a good question. I like that. Yeah. Um, well, in my field of research, which is epilepsy, I'm very interested into surgical treatments. So when you take out a part of the brain, you see a lot of these changes. A lot of them are kind of expected. So you will see after resection of the temporal lobe, for instance, you will see some of the areas nearby thin and atrophy, which makes sense because a lot of the connections have been destroyed. So the cells may just die, and then you see the cortex kind of thin. But what's surprising is that you see other sets of regions that are far away in the brain that actually grow thicker. So um, what's that about, right? So it's it's kind of strange to see, and it's cool to see that maybe there's some sort of adaptive plasticity or compensatory mechanism or recovery that's happening in response to something that's so invasive in the brain. So I always like to see this kind of like brain thickness kind of growing thicker than it was before surgery, and it's in adults. It's very unlikely that it's neurogenesis. So it's I don't think it's the creation of new neurons that's happening, but maybe the creation of new synapses or dendrites, because the brain is not in epilepsies. If you have surgery or successful surgery and you have less seizures or no more seizures, then perhaps these kind of brain regions that are bigger, they get reassigned to something more fun, like cognitive functions. Yeah, mood or anxiety related yeah mechanisms. So yeah. Yeah.
Good answer. Okay, maybe one final one. This one's a bit of a curveball. It's from the user Yadgar. I love it. I think I'm gonna ask this question to all my like future guests. So he asks, if you could scan the brain of any famous person, living or dead, who would it be, and what would you expect to find?
That's yeah, it's a pretty good question. I think I would go with like a living person, um, uh, just to see like you know, um, uh, yeah, ex vivo MRI is not really my thing, so I'm gonna go in vivo living human, and I would go for Sir David Attenborough. I think he's the one I would scan. He has so much knowledge. He's so charismatic. He's seen so many things that I think we might just find a new brain region altogether in his brain, or maybe he has like three hippocampi or something really cool, or maybe like a new functional network, like the wilderness network or something really cool. So yeah, I would go for him. Yeah, definitely. I don't know if he's one of your subscribers, but if he is, yeah,
You
I'd
should
like
be.
to, get in touch or get you a
I
scan.
love it.
Yeah.
Good stuff, Sarah. Good stuff. Amazing. I wasn't expecting that. All right, we did it, Sarah. Excellent. How was your experience on the show? You're my second guest ever, and I have to say, you're my second guest. This is the second episode, and already I would definitely put you at the top two guests of all time who have ever been on the show.
Well, right back at you, Shaheen. You're my first podcast experience, and you're number one so far. So, I I loved it. I think thank you so much for showcasing our work. This one really meant a lot to me, and it's nice that I get a platform to talk about it even more. And I'd be happy to answer any questions if people have them by email. Yeah, thank you so much, Shaheen.
It's been a pleasure. It's been an honor, Sarah. Thank you so much. It's funny. Right around this time at the lab, we used to put Christmas music and holiday songs and everything. And yeah, it's. I wish I had some like holiday memorabilia with me right now that I think of it. Maybe once I'm done with this and I edit it out, the closure music could be what was it, Dominic the Christmas donkey?
Yeah, yeah. There was a few. Yeah, there was a few of these songs that were. There was one about like uh, a reindeer hit their grandma, or what was it?
Yeah, yeah, yeah.
Yeah, I'm sure you
Something.
can find something
Yeah, yeah, yeah. Okay,
that
I'll
brings
I'll,
us
I'll think
back.
of something good. Well, speaking of Christmas and the holidays, do you have any plans?
Yes, eat, sleep, play outside, and stay away from my computer. Yeah.
Wonderful. That's excellent.
Yeah. What about
Good
you?
stuff. Well, I'm just gonna spend time with the family, wife, daughter, in-laws. Again, eat, rest, have good company, good friends, good family. Just have a good time. Yeah,
Perfect combo, my opinion.
exactly. Well, Sarah, ce fut un plaisir. Thank you so much once again. If you have any final words, any final thoughts to share with us, I give you the platform.
I mean, well, thank you first, Shaheen, for the invitation. And I just want to say that this work, I know I was the one talking about it today, but you're a co-author. You were an essential part of the study. But there's also many other authors that really made this work possible. And I love that in neuroimaging of epilepsy research, we're so keen to collaborate, and I hope that never changes, honestly. And I'm really looking forward to, now that I have my own lab and that we're collecting data, to pay everyone back with MRI data and start contributing our own very own data set. So yeah, I just want to say thank you to everyone that's been involved in this project, because it's been amazing, and there's many more to come, I think.
Amazing. What a great note to end things on. All right, Sarah, thank you so much, and we'll do it again.
Yeah.
Hey, jingity jing, it's Dominic the donkey. Jingity jing, the Italian Christmas donkey. La 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 la.